Yes, hello everyone. Today we are going to discuss about the topic interrupts of 8086. It is an important topic in 8086 microprocessor. So, what is mean by interrupts? Interrupt of the processor. Why we are using these interrupts? What are the uses of these interrupts? Why we are? What is the need of the interrupt? So, where we can use this? So basically interrupt is a signal sent by an external device to the processor so as to request the processor to perform a particular task. So it is a disturbance signal. So basically interrupting the normal execution of the program to perform a special task. So here we are getting that interrupt signal by using the external device. So one of the external device is sending some of the signal called as that interrupt signal to our the microprocessor. So that what is the external device have a particular task to perform that task given by the device. So we are interrupting the normal execution of the program that is performed by the microprocessor. So method 1, so we are having the three types of the uh, generating that interrupts to the microprocessor. So the first method that is called as interrupts, those are given as a hardware and software interrupts. So the method to that is by using vectored and non-vectored interrupts. So the method 3 that is using maskable and non-maskable interrupts. So there are the three classification of the interrupts. So here, so the hardware, what is meant by hardware and software interrupts? So when we are executing any of the what is that interrupts? That means here we are having in the pin diagram of the 8086 we are having some of the pins called as INTR and NMI. So INTR is already so called as interrupt request, and NMI is called as non-maskable interrupt. So when we want to execute, when we want to give the processor to generate that interrupts, so that is by requesting that microprocessor by the external device. So that is given by using that INTR pin. So when we are generating that interrupt by using this INTR pin and NMI pin, these are called as hardware interrupts because of generating that interrupts through the pins. So we are calling it as a hardware interrupts. So what is meant by software interrupts? Here by using that instructions. So already we know that software means the instructions, the programs where the instructions are written. So in that case, using some of the software instructions like INT and so INTN. So here we are generating that interrupts by using INTN instruction. So where N is called as a number, type number. Those are classified from 0 to 255. Total 256 types of the software interrupts are present. So when we are running the program, so we are generating that software interrupt. So by using some software instruction, so then what is that? We are executing that interrupts. So by using that interrupt service routine. So these type of interrupts are called as software interrupts. So hardware interrupts, we already know that if an interrupt initiated in a processor by applying an appropriate signal to the interrupt pin, then the interrupt is called as a hardware interrupt. So what is meant by maskable and non-maskable interrupts? Second case. So masking is preventing the interrupt from distributing the current program execution when the processor is performing an important job, and if the processor should not be interrupted, then all the interrupts should be masked or disabled. That means when we are generating in any processor, any other device is giving that interrupt request to our microprocessor, so it is the case of microprocessor to accept that interrupt or not. Okay, if it is accept means it should execute that interrupt. So here we are having the two cases here. It can be accept and it can be reject here. So when it is accepted, it should what is it is must, what is it, it should be executed first. So after that only, so we are executing that main program. So here maskable and non-maskable interrupts are in such a case that in the processor with multiple interrupts, the lower priority interrupt can be masked so as to prevent it from interrupting the execution of the interrupt service routine of higher priority interrupts. So we are having different types of the interrupts are also present. So when all the interrupts are occurring to the microprocessor at a time, so we have to give the priority to each of the interrupts. So first we have to service that higher priority interrupt. Next, after that, lower priorities interrupts. Like that, we are having, we are generating, we are servicing that interrupts. So what is the need of the interrupt here? So in general case, the process of interrupting the normal program execution to carry out a specific task is called as the interrupt here. So the processor can be interrupted by using different ways here. So the first case, by an external signal generated by the peripheral, by an internal signal generated by a special instruction in the program. So here, when we are giving the external signal, means it is one of the hardware type of the interrupt here. So when we are generating the special instruction, means it is one of the type of software interrupt here. So by an internal signal generated due to an exceptional condition which occurs while executing an instruction. When we are executing the microprocessor executing any instruction, so in that program itself, what is that, some of the signals are generated due to exceptional condition like divide by 0, and different exceptional conditions are present for that infinity case. Okay, so in that case, only that internal signals are only generated within the execution of that program. So these are the different ways how the processor can be interrupted. So whenever external device needs some service from the microprocessor, it places a request in the form of the interruption. So when the external device wants the bus access of the microprocessor also, so it is requesting that our microprocessor in the form of the interrupt to access the bus, master bus, and other also, like acting as a co-processors also. When a microprocessor receives an interrupt signal, it stops executing current normal program and saves the status of the various registers like code segment register and instruction pointer and flag register in 8086. So here, when the microprocessor is receiving that interrupt signal, first it is halting, that means stopping the current execution of the program and saving the status of the addresses of CS, IP and flag register into the stack memory here. In stack, and then the processor execute a subroutine or a procedure that is executed in response to an interrupt is also called as interrupt service subroutine. So whenever the processor is getting that interrupt, means how it is servicing that interrupt also very much matter here. So here it is servicing, basically all the interrupts are present in a table called as interrupt vector table. So in that interrupt vector table, each of the different interrupt has a different address. So already we know that in the 1 MB of the memory, here we are using 1 KB of the memory that is reserved for the storing of all the interrupts here. So each address, for each interrupt we are allocating a memory address also. So when one of the interrupt is got in the execution of the program, software program, then first what is that, it is checking for the interrupt vector table, and it is servicing that interrupt by using this interrupt service subroutine here. So it is meant by that interrupt means a specific task is present. When we are calling that interrupt, what is that, we are executing that interrupt. That means some of the instructions, the normally used instructions that is used in the program. So that is what we have to execute in a form of the called as interrupt service subroutine here. So at the end of the ISR, the stored statuses of registers in stack are restored to respective register, and the processor resumes the normal execution of the program from the point where it was interrupted. So that means after executing that interrupt that is present in the interrupt service subroutine, so the control should be transferred to the main program. So basically what is that, the control is transferring from the main program to ISR when the interrupt is occurred. So after execution of the ISR, it is again the control is moving to the main program. So that means here the normal execution of the program should be started where it was interrupted in the last case. So the classification of the interrupts of the 8086. So already we seen here, these are different types of interrupts are present for the 8086. In that, first one is called as hardware interrupts, second one is the software interrupts, and the third one, most important one, that is called as predefined interrupts are present. So what are the hardware interrupts here? The interrupts initiated by applying the appropriate signals to INTR and NMI pins of the 8086 are called as the hardware interrupts. So we already know that these are the pins. INTR and NMI are the pins that are present in the pin diagram of pin IC of the 8086. So here we are generating that interrupt by giving some of these signals to these pins, INTR pin and NMI pins. So then those type of the interrupts are called as hardware interrupts, because these are the hardware pins where we are applying the uh, interrupt. So the hardware interrupts are for the 8086 we are having, those are called as NMI and INTR. So already we know that NMI is called as a non-maskable interrupt, and whereas INTR is called as a maskable interrupt here. So maskable means the microprocessor should accept that interrupt and it should be serviced here. So that NMI is that non-maskable interrupt here. So it can be or cannot be so serviced here. So then NMI is a edge triggered on a low to high transition. So it is a edge triggered interrupt here, NMI. So the rising edge of the NMI is serviced at the end of the current instruction. So when we are using that low to high transition, when the interrupt is going from low to high transition, so in the high transition, that means mode it is when it is going from low to high, rising mode, in the rising edge of that clock pulse, that NMI is serviced first and at the end of the current instruction. So these are generated by using that next one is the software interrupts. So how we are generating the software interrupts? We know that they are generated by writing some of the instructions within the program here. So here we are generating the software interrupts by inserting some of the instructions called as INT instruction here in the program. So INT is called as a interrupt here. So the 8086 has 256 types of the interrupts are present. So where how we are denoting these interrupts, that is by using the instruction called as INTN. So where N is the number, the type of the interrupt. So it is ranging from 00 to FF. That is called as total 256 types of the interrupts are present. So the third case what we are having called as a predefined interrupts. So these are the most dedicated interrupts of the 8086. So we are having total 5 predefined interrupts are present. So the first one is called as type 0 interrupt, next one is type 1 interrupt, and the third one is type 2 interrupt, the fourth one is type 3 interrupt, the fifth one is type 4 interrupt. Type 0 interrupt is also called as divide by 0 interrupt. Type 1 interrupt is called as single step interrupt. Type 2 interrupt is called as non-maskable interrupt. Type 3 interrupt is called as a breakpoint interrupt, and a type 4 interrupt is called as overflow interrupt. So these all these predefined interrupts are occurring in the within the instructions where we are writing that assembly language program. So for when we are generating any of the interrupt, when these interrupts are including in the program, then some of the instructions are executed. So that means the processor execution will be changes when these interrupts will be occurred in the program. So we will see that what is maybe all these predefined interrupts here. So the first one is called as type 0 interrupt. So we know that it is also called as divide by 0 interrupt. So when it is executed in the program, so this interrupt is a non-maskable, and it is automatically interrupted whenever a division by 0 is attempted. So whenever we are getting the calculation in the part of the arithmetic calculation, when we are getting the divide by 0 operation, when we are having that any number by 0 operation within the program, then automatically the processor will be interrupted, and it should be executed first. That means so we are generating some of the interrupt, that is called as a type 0 interrupt here. So divide by 0 is called as a type 0 interrupt. So the next one we are having the type 1 interrupt. So it is also called as a single step interrupt here. So single step control is used for debugging assembly language programs. So where we are using this single step interrupt means for the case of the debugging, so to find the errors, so to decode the errors that is present in the assembly language program. So we are using the single step controlling mode of the 8086. So in single step control, the processor executes one instruction and then stops. That means, so when for example when we are having the 10 number of instructions are present in the program, so when we want to decode the errors those are present in the program, so we are generating this interrupt, that is a single step interrupt. It is also called as, that is when we are executing this, means this is executed when the trap flag is equals to 1. So you have to remember that when trap flag is set to 1, the processor is working under the single step execution mode here. So after every instruction execution, every instruction decoding, so we are executing the instruction, and also we can check the error that is present within the instruction itself here. That means after every instruction execution we are checking the errors here. So it is not possible when the trap flag is equals to 0 here. The trap flag should be set to 1 to execute that program in a single step mode here. So therefore after the contents of the registers and the memory locations can be examined to see the result after every execution of every instruction. So we can check the contents of each register and the memory locations also for the errors. So if the result is correct, the user gives the command to execute the next instruction. If the current executed instruction is perfectly present, that is the result is correct, that is present in the registers and the memory, then it is going, the control is transferred to the next instruction. So in the 8086, the trap flag is set to 1 to implement the single step controlling mode. So whenever the trap flag should be 1, okay, trap flag is equals to 1. So we have to know that 8086 is using single step controlling execution mode. The third one, that is called as a type 2 interrupt. It is also called as a non-maskable interrupt, NMI. So it is used for some of the emergency conditions. For example, it is used to save the program and the data. So whenever the power supply fails, okay, so whenever we are whenever executing that program, assembly language program, if the power supply failures occurs, then so automatically it stores the addresses and data into the memory, so that program and data should be saved. So that is whenever it is occurring, whenever we are getting that power supply fails, we are generating this type of interrupt called as non-maskable interrupt. So an external circuit is used to detect the power failure and send an interrupt signal to 8086 through the NMI pin here. So whenever the power failure occurs here, so some of the external circuit that is sending the interrupt signal to our microprocessor, so through the pin called as non-maskable pin, NMI pin here. So if AC power failure occurs, the DC voltage supply to computer may remain for 50 milliseconds due to capacitors provided in the filter circuits. Okay, so if the AC power alternating current power failures occurs, we are using the DC voltage. Going to DC voltage, it can have the charge of the power, that means up to 50 milliseconds. So in this time only we can save all the program and data to the memory here. So this time is sufficient to save the program and data, so in some RAM having the battery backup supply. So the program along with the data is restored when power returns and can be executed again from the point where it was interrupted. So here whenever that power came, that data, so program where we were stored, that means that is also restored here, and we can execute that again from the same point where we are executed when the power supply failure occurs here. So that is the case, the type 2 interrupt, that is also called as the non-maskable interrupt. So the fourth one, that is called as type 3 interrupt. So we know that type 3 interrupt is also called as a breakpoint interrupt. So this type 3 interrupt is occurred, that means produced by execution of the INT3 instruction. Directly we can also execute this instruction, so like INTN, so where N is called as a type number, so directly we can write that the type number, that is 3, so within the instruction INT3. So by using that we can execute this interrupt here. So a breakpoint is inserted in a program for debugging the assembly language program. So why we are using this breakpoint means, for example, we have a doubt of in the middle of the program. So how to break that execution? so without going to the next instruction. So that is by including one break point within the program where we are having some doubts here. So we can break that execution of the program within the total main program. So here we are breaking that breakpoint is inserting in the within the program, and for that is also used for debugging. The debugging means it is used to detect the errors also. So the system executes all the instructions so up to the breakpoint and then stops the execution. So for example, we are having the 10 number of instructions we are writing within the program. So in that case, for example, we want to execute up to 5 instructions only, and we have to see the result if any errors are occur, or any errors are present within those 5 instructions also. So in those cases, what is that, we are using this breakpoint, and the processor can execute up to that 5 instructions, up to the 5 instructions where breakpoint is included. Then it is checking for the errors. So is there any errors are present in that execution? So by that one, it is if it is the errors are present, it is rechecking, and we can also edit the program. Otherwise, it can also goes to the next line of the main program. So depending on the system, the register contents may be displayed on the CRT, or in a simple system, the control is returned to the user here. So depending upon our register, the system registers also, we can also display all the data that is stored in the register. The temporary results, those are stored in the temporary registers by using that CRT, and the control is again transferred to the return to the user here. So this is the type of interrupt called as a breakpoint interrupt, is the type 3 interrupt here. The fifth one, that is called as a type 4 interrupt here. The type 4 interrupt is also called as overflow interrupt. So here we can also have one of the instruction, that is INTO here. So in the directly we can have that condition. It is called as a conditional unconditional branch instructions. That means without any condition is checking, that control is automatically so transfer to that interrupt here. So when this interrupt is occurred here, so the 8086 overflow flag is set to 1 if the signed result of an arithmetic operation on two signed numbers is too large to represent in the destination register or memory location. So whenever the overflow flag is set to 1, okay, so the signed result of the arithmetic operation, that means overflow flag is set to 1 means we are generating that interrupt, that is INTO interrupt. So when this overflow flag is set to 1, so here when we are performing any arithmetic operation like addition or multiplication, so here when we are adding that two 8-bit numbers, so then there is a choice of getting that result also, having that 9th bit also, or else when we are executing any two multiplying any two 8-bit numbers, we can get a number that is having more than 8 bits here. That means we cannot store that in the 8-bit register. That means, so here it is a too large, the result will be too large to store in that destination register. So in that, within that case, we are generating a flag, that is overflow flag, that is going to set to 1 here. So to implement the type 4 interrupt here, INTO instruction is inserted in the program immediately after the arithmetic operation. So after every arithmetic operations like addition, subtraction, multiplication and division, so we are inserting one instruction called as INTO instruction. So here it can check if that overflow flag is set to 1, so after that arithmetic operation, so based on the result, it can be going to the overflow flag is going to set to 1 or reset to 0. By that INTO will be enabled or disabled. So if the overflow flag is not set, the INTO instruction simply performs no operation. There is no operation will be performed if it is reset. So if overflow flag is set, the INTO instruction performs the type 4 interrupt here.